Hello students, welcome to part 1 of chapter number 2, Data Representation. In this session, we are going to learn about data representation. It means that what is data and how it can be represented in the computer system. And in the second part, we will learn about what are the number systems available in digital computer. And in the third part, we will learn about different types of number conversions like a decimal to other number conversion methods and binary to other number conversion methods. Students, now we will start with the introduction part of data representation. What is mean by data? You all know about it, right? In the lower classes and junior classes, you have studied about data. Data means information, and we used to show different types of data like text, graphics, sounds, and computer use different types of numeric codes to represent these data. So data representation refers to the internal method used to represent different types of data inside the computer. So here is the number system. As I told you, different types of data stored in the computer as numbers. So number system is a way of representing numbers. In digital representation, various number systems are used. The most common number systems used are decimal, binary, octal and hexadecimal systems. Each number system is uniquely identified by its base value or radix. Base is the count of number of digits in each number system. Let's learn about these number systems one by one. First number system is decimal system. It is composed of 10 numerals or symbols. Here deca means 10. That's why this system is called as decimal system. And these 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. By using these symbols, we can express any quantity. And the decimal system also called the base 10 system because it has 10 digits, and it is a positional value system in which the value of a digit depends on its position. This means that each digit in the number is multiplied by 10 raised to a power corresponding to that digit's position. And this is illustrated in the figure where the number 2512.1971 is represented. The decimal point separates the positive powers of 10 from the negative powers. The number 2512.1971 is thus equal to 2 into 10 to the power of 3 plus 5 into 10 to the power of 2 plus 1 into 10 to the power of 1 plus 2 into 10 to the power of 0 plus 1 into 10 to the power of minus 1 plus 9 into 10 to the power of minus 2 plus 7 into 10 to the power of minus 3 plus 1 into 10 to the power of minus 4. In this digit, 2 carries the most weight, so it is referred as most significant digit, in short MSD, and 1 carries the least weight and is called the least significant digit, in short LSD. And the second number system is binary system. In the binary system, there are only two symbols used there, 0 and 1. So this system is called as base 2 system. The binary system is also a positional value system wherein each binary digit has its own value or weight expressed as a power of 2. This is illustrated in this figure. Here, places to left of the binary point are positive powers of 2 and places to the right are negative powers of 2. The number 1010.0101 is represented in this figure. To find the decimal equivalent of this number, we take the sum of the products of each digit value, that means 0 or 1, and its positional value. And the third number system is octal. This number system is important in digital computer. It has a base of 8, meaning that it has 8 unique symbols. They are 0, 1, 2, 3, 4, 5, 6, 7. Each digit of an octal number can have any value from 0 to 7. The octal system is also a positional value system, wherein each octal digit has its own value or weight expressed as a power of 8. The places to the left of the octal point are positive powers of 8 and places to the right or negative powers of 8. The number 3721.2406 is represented in this figure. The last, that means the fourth number system is hexadecimal system. It uses base 16, thus it has 16 possible digit symbols. It uses the digits 0 to 9 and A to F. Note here that the decimal numbers 10 through 15 are represented by the letters A through F. The hexadecimal system is also a positional value system, where each hexadecimal digit has its own value or weight expressed as a power of 16. Students, in the previous section we learnt about different number systems used in computers. A decimal number system is most commonly used by humans, but digital systems understand binary numbers, whereas octal and hexadecimal number systems are used to simplify the binary representation for us to understand. Now let us learn how to convert a number from one number system to another number system for better understanding of the number representation in computers. Now we will learn conversion from decimal to other number systems like decimal to binary, decimal to octal, and decimal to hexadecimal. Students, in decimal conversions, decimal to binary is the first conversion method that we are going to learn now. There are two procedures for converting decimal to binary. They are sum of powers of 2 method, and the second one is repeated division method. Now we convert the decimal number 200 to binary number using the sum of powers of 2 method. For this, first we have to find the largest power of 2 from the table without exceeding 200. 128 is the largest number without exceeding 200, right? And here 2 to the power 7 is equal to 128. So put 1 at 8th position and 0 at all other positions. So 128 decimal value is equal to 10000000 binary value. Repeat this process for the remainder and continue until the remainder is 0. Then subtract this 128 from 200 and then you will get answer 72. From the table 64, that means 2 to the power of 6 is the largest number without exceeding 72. Put 1 at 7th position and 0 at all other positions. Now subtract 64 from 72. Answer is 8. From the table 2 to the power 3 is equal to 8 and it is the largest number. So put 1 at 4th position and 0 at all other positions. Finally add all the binary numbers and it is equivalent to the binary equivalent of 200 is 11001000. So that is our answer. Students, now we are going to use repeated division method to convert decimal to binary. In this method, number is successively divided by 2 and its remainders recorded. Let us now convert our decimal value 85 to its binary value. First divide the decimal number 85 by 2, quotient 42 and remainder 1. Now divide 42 by 2, we get quotient 21 and remainder 0. Continue this process till quotient is equal to 0 or lesser than 2 and write the remainders from bottom to top. The binary equivalent of 85 is 1010101 and that is our final answer. Now we are going to convert decimal fraction to binary. To convert integer part of decimal fraction to binary, we use repeated division method. In this method, integer part is successively divided by 2 and its remainders recorded. To convert decimal fraction into binary, multiply the decimal fraction by the base, that's 2. Do until you will get 0 at a fractional part. And here you have an example 85. You have to convert 85.375, that is a decimal number, to its binary value. And here we have used repeated division method for the integer part, that is 85, and it is recorded. The remainders recorded here. That is 85 is equal to 1010101. So decimal number 85 is equal to 1010101 binary value. And now we have to convert the decimal fraction. For that, the decimal fraction 0.375 multiplied by 2 and the answer is 0.750. Here we have to record that integer part. Here integer part is 0. That must be recorded, and we have to continue with the decimal part. Here 0.750 is the fractional part and it is multiplied with 2 and answer is 1.50. As usual, integer part is recorded. Here 1 is an integer, it is recorded, and we are going to continue with the 0.50 fractional part and it is multiplied by 2. Answer is 1.00, and as usual integer part is recorded, that is 1. So here we reached 00, fractional part is 00. So here we are going to stop our process, and at last we are going to record all the integer portion, that is 0, 1, 1, that must be recorded. So the binary equivalent of 0.375 is equal to 0, 1, 1. At last we are going to combine these 85 and 0.375. So 85 the decimal number 85.375 is equal to 1010101.011. Students, here's the next conversion method, that is decimal to octal, and decimal number can be converted to octal by repeated division method and with the division factor of 8. Octal means 8, so here we are going to use 8 for division. And here is an example 266. This is the decimal value and we have to find out octal equivalent of this number. For that we are going to divide 266 by 8 and we get quotient as 33 and the remainder 2. Again we are going to continue with the 8. We are going to divide 33 by 8. Quotient is 4 and the remainder is 1. It is lesser than the quotient value. 4 is lesser than 8. So obviously quotient will be 0 at last and the remainder will be 4. And we have to record these remainders. That means 412. So 266 is equal to 412 octal value. Students, here is the next number conversion method, that is decimal fraction to octal. We use repeated division method to convert integer part into binary. In this method, number is successfully divided by 8 and its remainder recorded. To convert decimal fraction into binary, multiply the decimal fraction with 8 until you get 0 at fractional part. For an example 266.20, this is a decimal fraction value. It must be converted to its octal equivalent value. First we have to take an integer part, that is 266, and we have to use repeated division method here, and we are going to divide 266 by 8, and we will be getting 412, that is octal value of 266. And now we have to take a 0.20, that is fractional part of this decimal number. It must be multiplied by 8, and answer is 1.60. And look at the integer part, 1 is there, right? So it must be recorded. And 0.60, we have to continue with the 0.60 fractional part. It is multiplied by 8, and answer is 4.80. 4 is the integer part, 4 is recorded, and 0.20 is taken, and it is multiplied by 8. 6.40 is the answer. 6 is integer part, and it is recorded. 0.40 into 8. Next one, answer is 3.20, and the integer part is 3. It is recorded. And look at the fractional part of this number, 0.20. It is repeated, right? So we need not continue with the process. Here we can stop our multiplication. So the final answer will be 266.20. Decimal value is equal to 412.1463 octal value. Students, here is the next conversion method, that is the decimal to hexadecimal. A decimal integer can be converted into hexadecimal by repeated division method with a division factor of 16. Students, recall that we did decimal to binary conversion using repeated division by 2, and decimal to octal using repeated division by 8. Likewise, decimal to hexadecimal conversion can be done using repeated division by 16. For an example, 423, this is our decimal value. We are going to convert this decimal value to hexadecimal value. For that, we are going to divide this decimal value by 16, and quotient is 26 and the remainder is 7. It is recorded, and 26 is divided by 16, and quotient is 1 and the remainder is 10. So here we are going to write capital letter A, and 1 is lesser than 16. So it will be, obviously the quotient will be 0 and the remainder will be 1. And we have to write down these remainders from bottom to top, 1A7. Students, here is the next number conversion method, that is decimal fraction to hexadecimal. We use repeated division method to convert integer part into binary. In this method, number is successfully divided by 16 and its remainder recorded. To convert decimal fraction into binary, multiply the decimal fraction with 8 until you get 0 at fractional part. For an example, 423.03125, this is a decimal value. It has to be converted to hexadecimal value. For that, we are going to take integer part, that is 423. It is divided by 16, and we are getting the value as 1A7. And now multiply the fractional part 0.3125 with the by 16. Answer is 0.5. Integer part is recorded. Integer part is 0. It is recorded, and 0.5 is multiplied by 16, and answer is 8.0, and integer part is 8. It is recorded. So here fractional part is 0. We cannot continue, we cannot do further, and we are going to record this number 0.08, that is the hexadecimal value. So the final answer is 423.3125. Decimal value is equal to 1A7.08 hexadecimal value. Students, so far we did conversion from decimal to other number system. Now we are going to do conversion from binary to other number system. So these are the things we are going to do. These are the conversion we are going to do: binary to decimal, binary fraction to decimal, binary to octal, binary fraction to octal, binary to hexadecimal, and finally binary fraction to hexadecimal. Students, now we are going to learn binary to decimal conversion. There are two methods to convert a binary number to decimal number. They are position notational method and double, that means a doubling method. First we will study about positional notation method. As I told you earlier, binary system is a positional value system. That means weight of the positions from left to right increase by 1. So the positional values are 2 power 0, 2 power 1, 2 power 2 and so on for the integer part. And weight of the positions from left to right decrease by 1. It means the positional values are 2 power minus 1, 2 power minus 2 and so on. And here we have an example. In this example, we have to convert a binary number 11011 to decimal number. The positional weights for each bit position is 1 into 2 power 4 is equal to 16. Likewise, 1 into 2 power 3 is equal to 8 and 0 into 2 power 2 is equal to 0 and 1 into 2 power 1 is equal to 2. And at last 1 into 2 power 0 is equal to 1. When we add all these values together, we will get a decimal number, that is 27. So answer is 11011 base of 2 is equal to 27 base of 10. Students, here is the next number conversion, that is binary to decimal conversion. As we have studied earlier, we have two methods on it. Now we are going to use the second method, that is the doubling method. This is a simple one. To convert binary number to decimal number, we need to start from the leftmost digit from the input. Here in this example, 11011, this is our binary number. We have to convert this binary number into decimal number. For that, we are going to take the leftmost digit, that is 1, multiply this number by 2 and add the next bit, that is 1 is equal to 3. Now multiply this result 3 by 2 and add the next bit 0. It is equal to 0. It is equal to 6 and multiply by 2. That means 6 into 2 plus 1. Next bit is equal to 13. 13 into 2 plus 1 is equal to 27. So the final answer is equal to 27. This is the decimal number. Since we are doubling each time, that means multiplying by 2. Right? So this method is known as doubling. So here is the next number conversion method, that is binary fraction to decimal. To convert binary to decimal, add positional weights or values with power of 2. Start from right side. To convert binary fraction into decimal, take the sum of products of each digit value and its positional value. Start from left side. For example, convert binary number 11011.0101 to its decimal value. The positional weights for each bit position is 1 into 2 to the power 4 is equal to 16 and 1 into 2 to the power 3 is equal to 8. 0 into 2 to the power 2 is equal to 0. And 1 into 2 to the power 1 is equal to 2. 1 into 2 to the power 0 is equal to 0. 0 into 2 to the power minus 1 is equal to 0. And 1 into 2 to the power minus 2 is equal to 0.25. And 0 into 2 to the power minus 3 is equal to 0. And 1 into 2 to the power minus 4 is equal to 0.0625. When we add all these values together, we will get your decimal number 27.3125. So answer is 27.3125. Now we are going to learn next number conversion, that is binary to octal. To convert a binary number into octal number, first take the binary number, divide the binary digits into groups of 3 starting from right for integer part and start from left for the fraction part. Convert each group of 3 binary digits to one octal digit. For example, convert binary number 1010111100 to octal number. The integer part of a number is divided into groups of 3 digits. In this case, number of bits in a binary number is not multiple of 3. Multiples of 3. So 2 zeros are added on the most significant position of the binary number. Now write the octal number for each 3-bit group from the table. Octal value of 001 is 1. Octal value of 010 is 2. Octal value of 111 is 7. And 100 is equal to 4, and the record octal equivalent is 1274. The next number conversion is binary fraction to octal. To convert the fractional binary number into octal value, substitute groups of 3-bit and integer part by the corresponding digit. Similarly, make groups of 3-bit for fractional parts starting from left to right and substitute each group by its equivalent digit or symbol in octal number system. Add zeros at the end of the fractional part to make a perfect group of 3 bits. And here in this example, we have to convert binary number 0110.1011 to octal. The integer part of the binary number is divided to groups of 3 bits and single zero at MSB is ignored. Likewise, the fractional part of the binary number is divided into groups of 3 bits. 2 zeros are added at LSB to make it complete groups of 3 bits. Octal value is taken from the table and the record octal equivalent is 63.54. Now we are going to learn the next number conversion, that is binary to hexadecimal. To convert a binary number into hexadecimal number, first take the binary number, divide the binary digits into groups of 4 starting from right for the integer part and start from left for fraction part. Convert each group of 4 binary digits to one hexadecimal digit. For example, convert binary number 10101011010001 to hexadecimal value. The integer part of binary number is divided into groups of 4 digits. In this case, number of bits in a binary number is not multiple of 4. So 4 zeros are, 3 zeros are added on the most significant position of the binary number to make it complete groups of 4 bits. Now write the hexadecimal number for each 4-bit group from the table. Hexadecimal value of 001 is 1, hexadecimal value of 0101 is 5, and hexadecimal value of 0110 is 6, and 1001 is equal to 9. Hence the record hexadecimal equivalent is 1569. And here is the next number conversion, that is binary fraction to hexadecimal. To convert the fractional binary number into hexadecimal value, substitute groups of 4-bit in integer part by a corresponding digit. Similarly, make groups of 4-bit for fractional part starting from left to right and substitute each group by its equivalent digit or symbol in hexadecimal number system. Add zeros at the end of the fractional part to make a perfect group of 4 bits. Here in this example, we have to convert binary number 00110001.110111 to hexadecimal. The integer part of the binary number is divided to groups of 4 bits and single zero at MSB is ignored. Likewise, the fractional part of the binary number is divided into groups of 4 bits. 2 zeros are added at LSB to make it complete group of 4 bits. Hexadecimal value is taken from the table and it is recorded. The record hexadecimal equivalent is 65.DC. Students, here is a summary of today's session. Today we learned about data representation and digital numbers. We have digital numbers to represent data, and number conversion. We have studied 4 different types of number system, that is decimal, octal, binary and hexadecimal, and how can we convert these numbers from one system to another system. And we have studied only 2 methods, that is decimal to other number system and binary to other number system. There are some more. We will learn about those methods in the next session. Students, here you have 6 questions related to our topic. First one is, what does the base of a number system mean? Second one, which digits are used in hexadecimal number system? Third one, convert the decimal number 781 to its binary equivalent. Fourth one, convert the binary number 1001.010101 to its hexadecimal equivalent. Fifth one, convert binary number 101101.001 to its decimal equivalent. Sixth one, convert the decimal number 231.12 to its octal equivalent. Go through the lesson and find out the answer. With this, we come to the end of the session. Thank you, students, and I'll meet you in the next session. Until then, take care and bye.